All right. Hi there, folks. Welcome to our last lesson on electrochemistry. In fact, this will be our last lesson, our last video lesson anyways, for this semester and for you throughout the rest of the year. So we've been working on this electrochemistry, this idea of these redox reactions, these oxidation or reduction reactions where we're having one species undergo a reduction, where they're gaining electrons, one species undergoing oxidation where they're giving up electrons, and really we're seeing this change in charge, or this change in oxidation state as that's happening. And scientists have known about this property and these redox reactions for over 200 years. Okay, in fact, our first batteries were created in early 1800s, and batteries rely on this idea of these redox reactions. And we use these in these things called these electrochemical cells. Okay, and so this is a similar drawing to what you have on your notes right now with a little bit more information than what I've given here. So I'm just going to start to fill in the missing pieces that we have. Okay. So as we know, with all batteries, we have a positive end and a negative end. We have an anode and a cathode. Okay, and so we want to understand a little bit more about how does that apply to our redox reactions, since that's what we're dealing with here. Okay, so what I have is I have these electrolytic solutions in these two beakers. Okay, on this side I've got copper sulfate, so copper 2 plus and sulfate ions 2 minus, and over here I've got zinc sulfate, which will give us zinc 2 plus and sulfate ions in solution. Now, we choose for these solutions fully soluble solutions. So in this case, because of the metals I've chosen, sulfates work. A lot of times though, we will see those nitrates in there as we see in our next example. Okay, but for this one, we're just using these sulfates. We have these nice ionic, fully dissolved solutions for this 1 molar solutions that we're dealing with. Okay, and that part is important. These electrochemical cells and the standard reduction potentials that we see in the textbook are based on 1 molar solutions at 25 degrees Celsius. Okay? And so what we have here inside these solutions is in our copper solution, I've also got a piece of copper metal. Okay, so we can either call that our pole or our node. Okay, and we've got to figure if that's going to be an anode or a cathode. And then similarly inside our zinc solution, I also have a zinc pole in here as well. Okay, so again, one's going to be a negative pole, one's going to be our positive pole, and although you have that on your notes, I want to kind of talk through how we can figure that out based on the situation. Okay, 2 other pieces that we have here, we have this salt bridge. Okay, we're going to talk about those ions transferring back and forth in there as well, but essentially, if electrons are going to be flowing, we would end up with one of these sides being very positive and one side being very negative. And eventually, if it's too negative, we wouldn't have those electrons flowing anyways. It would be repelled by that negative charge. So this salt bridge allows for anions and cations to transfer back and forth to balance out those charges or those electrons flowing. Okay, and the salt bridge will either be an inert situation like we have in here. We've got KCl, unreactive in both situations, and a fully soluble salt, or sometimes we would see a sulfate bridge since we have sulfates in solution, or if we have nitrate solutions, we might see a nitrate bridge. But either way, that salt bridge is just to allow for the balancing of the charges. Okay. Next up, we're going from one pole to the other, or in this case, from our zinc piece of metal to our piece of copper metal. We have a wire, and it's going through a voltmeter or something that's going to draw some voltage, so we can measure what that voltage would be. Okay, and we've got to figure out which direction our electrons are going to flow. Okay, so there is a typo on our sheet here, but we want to pay attention to 2 things. We've got 2 reactions happening here. So we've got this, we can have a Cu2 plus 2 electrons going to copper metal, or we can have our zinc 2 plus 2 electrons going to zinc metal. Okay, now obviously both of these are our reductions. We're going from a 2 plus charge to a 0. So these are reductions, but for a redox, it's going to go, one's going to be the reduction, one's going to be the oxidation or the reverse reaction. In order to find that out, we've got to take a look at our standard reduction potential. And when we do that, we realize that copper is higher up than zinc is on that list, which means then that copper is going to undergo the reduction and zinc is going to undergo the oxidation. So we're going to need to flip this reaction around. And essentially what we're going to do is we're going to have the zinc is going to go to 2 electrons plus that zinc ion. Okay, so now we have a reduction reaction combined with an oxidation reaction, and that allows us to combine to form a spontaneous reaction, and that's what we need for this cell to happen. Okay. So since this is our combined reaction, this will help us to understand which direction our electrons are going to flow from. So my copper solution is going to accept the electrons to get copper metal, and our zinc metal is going to give up electrons to go to the zinc ions. Okay? Well, if zinc metal is giving up those electrons are going to flow down this wire. Okay, to join into this side here. Those electrons can combine with the copper metal to form more copper metal on this pole, and the zinc metal, as it's giving up those electrons, will deposit more zinc ions in this solution. Okay, and that is how we're starting off with these reactions. So now that we know what direction our electrons are going to flow, we can start to figure out our positive and our negative poles. Well, if our electrons are leaving here, that means that this side is our negative pole, and our electrons are going here into that positive, right? Because that positive end is extracting those electrons, and that negative side is giving up those electrons, okay? And then just like we have our anions are negative and our cations are positive, we end up with our negative pole being our anode and our positive pole being our cathode. Okay, and we also know then, as we figured out from our reactions that helped us to figure out our electron flow, our cathode, well, that's this reaction happening right here. So this is our reduction reaction. And that makes our anode our oxidation reaction. Okay. So hopefully that helps explain that diagram. There is a lot of variety in how these diagrams can be drawn or created. So I encourage you to take a look at the examples in the textbook and possibly just look at a few of the different cells that you can find online to help give yourselves a better understanding of what's going on. Okay. All right. Taking a look at our second example here, this one I want to talk about not only just the setup of our diagram, but also talk about the flow of the anions and cations through the salt bridge. So taking a look at a second example, I'm looking at a silver solution and a magnesium solution. Once again, in my silver solution, I have a piece of silver metal. In my magnesium solution, I have a piece of magnesium. Now this time I have a slightly different solution. I'm using magnesium nitrate and silver nitrate, both fully soluble. And so I'm also using then a sodium nitrate salt bridge to help balance out these flow of electrons. Okay. Once again, we want to figure out what direction these electrons are going to flow. So if we take a look over here at our two half reactions, and again, paying attention to our standard reduction potential chart, we notice that silver is quite a bit higher than magnesium. So we are going to maintain the reduction in our silver, and we are going to have an oxidation happening in our magnesium. So this magnesium will turn and be the electron donor of these two pieces of metal. Okay, now both of these reactions, hopefully you remember from the video we posted last week discussing the different types of solutions in different metals. We had silver, magnesium, copper, zinc, and lead all in solution. and just seeing which ones formed reactions. Okay, for this one in particular, we noticed that silver always underwent this reduction and magnesium always underwent the oxidation based on the 5 metals we dealt with. Okay, so you just want to make sure you can compare those and start to realize how these ideas are connected. All right, now, since we know that magnesium is the one that's going to be undergoing the oxidation, right? We're going to go from a 0 charge to a +2 charge. That means it's going to be that electron donor, and electrons are again going to flow in this direction. Okay? That makes the magnesium our negative anode and makes our silver our positive cathode. Okay? And now we need to kind of understand what's happening in this situation. So electrons are that negative charge. As electrons are flowing, we'd end up with a buildup of negative charges over here, and that would result in a positive charge being built up on this side. And if we had too much buildup of negatives over here, the electrons wouldn't flow in this direction anymore. We would start to see a reversal, and then that doesn't really help with this spontaneous reaction and making electricity from this battery. We would just reach an equilibrium and have no charge whatsoever. So in order for this to happen, this is where the salt bridge comes into play. So if electrons are going into this side, we would start to see a buildup of negative charges here. Well, what happens then is that these NO3 ions, I'll add that in here, NO3 minus, these nitrates are going to start to flow in this direction here, okay? To help replace that negative charge that's being lost by those electrons transferring. Okay, or to counteract the positive buildup in this side. And so if we're getting a buildup of negative ions in here as well, we would start to have this positive sodium start to flow in this direction. Okay, so mostly we're concerned with understanding the flow of electrons to help this redox reaction and create this battery. Electricity is just the flow of electrons, so these redox reactions are perfect for creating that flow of electricity or those batteries. Okay, but we've got to have this salt bridge to help counteract those charges. So if our electrons are going to flow from the anode to the cathode, okay, what we're going to see in that salt bridge is in the salt bridge, our cation ions are going to flow to the cathode, and in the salt bridge, our anions are going to flow to the anode. Okay, so those are a couple different examples of how to draw these charts and how to understand these electrochemical cells. So hopefully that helps. Okay.